A ship disappears beneath the ocean's surface on purpose. It sinks itself controllably, deliberately, until only its deck remains visible at waterline. Then it slides an entire oil platform, weighing 50,000 tons, over its submerged hull. Then it pumps itself back up, lifting the platform clear of the water and carries it across an ocean. How does a vessel engineered to float deliberately fill itself with enough water to sink 30 meters below the surface without actually sinking? How do you move a structure the size of a 40-story building across open ocean on the deck of another vessel? And how does this ship maintain stability when the weight it is carrying exceeds the weight of most naval warships in the world? The answers involve ballast engineering borrowed from submarine technology, dynamic positioning systems accurate to within 10 centimeters in open ocean, and deck structures capable of supporting loads that no conventional cargo ship in history was designed to handle. You have seen cargo ships. You have never seen anything like this. Here is how a semi-submersible heavy lift vessel actually works. Let's start with the raw numbers, because the scale of these vessels redefines what the word cargo actually means. The largest semi-submersible heavy lift vessel currently in operation is the Pioneering Spirit, operated by Allseas Group. It measures 382 meters in length and 124 meters in width. 382 meters long. That is longer than the Empire State Building is tall, at 443 meters to its antenna tip, and the Pioneering Spirit is nearly as long measured horizontally. Its deck width of 124 meters means you could park approximately 40 standard shipping containers side by side across its beam. The Pioneering Spirit has a maximum lift capacity of approximately 48,000 tons for topsides removal operations. 48,000 tons. That is heavier than the USS Gerald R. Ford, the United States Navy's most advanced nuclear aircraft carrier, which displaces approximately 100,000 tons fully loaded, but carries a flight deck structure of approximately 45,000 tons. The Pioneering Spirit can lift the equivalent of a naval aircraft carrier's flight deck in a single operation. The vessel itself displaces approximately 900,000 tons of water when fully ballasted down. 900,000 tons of displacement. The RMS Titanic displaced approximately 52,000 tons. The Pioneering Spirit displaces 17 Titanics worth of water during ballasting operations. Its total deck area covers approximately 46,000 square meters, roughly equivalent to 6.5 American football fields of usable cargo deck. For standard heavy lift operations, the Dockwise Vanguard, another major semi-submersible heavy lift vessel, holds a cargo capacity of approximately 110,000 deadweight tons. 110,000 deadweight tons. That exceeds the cargo capacity of most of the world's largest conventional bulk carriers. The Dockwise Vanguard measures 275 meters in length, longer than 3 American football fields end to end, with a submersible deck that can accommodate cargo over 275 meters long and 70 meters wide simultaneously. Semi-submersible heavy lift vessels operate at submerged depths of 10 to 30 meters during loading operations. 30 meters of submersion, that is deeper than a 10-story building is tall, measured downward from the waterline. The vessel lowers itself to this depth by flooding its ballast tanks with seawater, sometimes taking on over 200,000 tons of ballast water, then pumps all of that water back out to resurface with the cargo secured on deck. A single heavy lift operation, submerging, loading, resurfacing, and securing cargo, typically takes between 24 and 72 hours of continuous precision ballast management. The fuel consumption of these vessels at operational speed reaches approximately 150 to 200 metric tons of heavy fuel oil per day. At an average fuel price of $600 per metric ton, daily fuel cost alone reaches $90,000 to $120,000, before crew, port fees, insurance, and operational costs are added. So how does a ship deliberately sink itself to a controlled depth and return to the surface without becoming an uncontrolled disaster? The engineering mechanism is as counterintuitive as it sounds. The fundamental principle is identical to submarine ballast technology, but applied in reverse and at a scale that submarines never approach. A conventional submarine dives by flooding ballast tanks to achieve negative buoyancy, sinking below the surface. A semi-submersible heavy lift vessel does the same thing, but it never loses its connection to the surface entirely. The vessel maintains positive buoyancy at all times through its twin pontoon hulls and stabilizing columns. Think of it like a table being partially submerged in a bathtub. The tabletop, representing the cargo deck, descends below the water surface, but the table legs, representing the stability columns, remain above water, keeping the structure connected to the air above. The table cannot sink because its legs prevent complete submersion. The stability column system is the engineering core of the entire vessel design. Semi-submersible heavy lift ships use twin parallel lower hulls, called pontoons, connected to the upper deck by multiple large-diameter vertical columns. The pontoons provide the primary ballast volume. The columns provide the stability interface between the submerged pontoons and the above-water deck structure. The MV Blue Marlin, a well-documented semi-submersible heavy lift vessel, uses two pontoons, each approximately 180 meters long and 14 meters wide, connected to the cargo deck by 8 stability columns, each approximately 8 meters in diameter. Each column has 8 meters of diameter, roughly the internal diameter of a large highway tunnel. These columns must simultaneously transfer the structural load of the cargo above, resist dynamic wave forces from all directions, maintain watertight integrity under 30 meters of external water pressure, and allow controlled ballast water movement between pontoon and column sections during the submersion sequence. Surprising fact number 1. The submersion sequence requires precise sequencing of up to 40 separate ballast tank valves in a specific order, because flooding tanks in the wrong sequence creates differential trim that can cause the vessel to list uncontrollably. Each ballast tank must be filled at a controlled rate, matched against simultaneous filling of mirror image tanks on the opposite side, while the vessel's trim control system continuously monitors heel and trim angles to within 0.1 degrees of level. The entire sequence is managed by computer systems running flooding scenarios in real time, but requires human operators approving each step, because the consequences of an uncorrected error at 20 meters of submersion are potentially catastrophic and irreversible. Surprising fact number 2. When submerged to 30 meters and ballasted with 200,000 tons of seawater, the vessel's stability depends entirely on the metacentric height calculation remaining positive throughout the loading operation. Metacentric height is the engineering measure of a floating vessel's tendency to return to upright after being tilted by a wave or wind force. A positive metacentric height means the vessel self-rights. A negative metacentric height means the vessel capsizes. When a semi-submersible is at maximum submersion depth, its metacentric height is at its minimum value. It is at its most vulnerable to capsize from external forces. The loading window, the period when cargo is being positioned over the submerged deck, must be completed within weather. Windows where wave height and wind speed stay below defined thresholds that the naval architects calculated as the stability limits for that submersion depth. Surprising fact number 3. The cargo is not mechanically attached to the deck during transport across open ocean. Oil platforms and other large structures carried on semi-submersible vessels are secured using a combination of custom-engineered seafastening frames. Steel structures welded to both the cargo and the vessel deck, grillage systems that distribute point loads across the deck surface, and chain lashing systems tensioned to specific loads using hydraulic tensioning equipment. The cargo sits on these supports and is lashed to the deck. It is not bolted through the deck. The integrity of an entire 50,000-ton cargo across thousands of kilometers of ocean depends on the engineering of the grillage and lashing system, and on keeping sea states below the design limit. The dynamic positioning system is what separates a modern semi-submersible heavy lift vessel from every previous generation of marine heavy transport, and it is where the most extreme precision engineering in these operations actually lives. During loading operations, when the vessel is submerged to 20 to 30 meters and positioned under a fixed offshore structure, the vessel must maintain its position to within approximately 1 to 2 meters of a fixed geographic coordinate in open ocean. Without this precision, the submerged deck cannot be aligned with the support points of the cargo above it. The pioneering Spirit uses a dynamic positioning system with 12 azimuthing thrusters, propulsion units that can rotate 360 degrees to push the vessel in any direction, producing a combined thrust of approximately 95,000 kilowatts. 95,000 kilowatts of thruster power. That is comparable to the propulsion power of a medium-sized nuclear submarine, dedicated entirely to holding a 382-meter vessel stationary against ocean current, wind, and wave forces simultaneously. The thruster control system updates its commands approximately 10 times per second, continuously recalculating the thrust vector required from each of the 12 units to maintain position within the defined tolerance. Position reference for the dynamic positioning system comes from multiple independent sources simultaneously. GPS provides global position to approximately 3-meter accuracy. Differential GPS corrects this to approximately 10-centimeter accuracy. Acoustic position reference beacons placed on the seabed directly beneath the vessel provide independent position data unaffected by satellite signal issues. Gyroscopes and motion reference units measure the vessel's heading, roll, pitch, and heave in real time. All 4 systems feed their data into the positioning computer, which identifies and discards any sensor that deviates significantly from the consensus of the others. The 2010 pioneering Spirit operation to remove the Troll A platform's jacket, a structure weighing approximately 40,000 tons, demonstrated the precision required in these operations. The vessel had to maintain position within 2 meters of target coordinates during a 6-hour lifting window, while managing changing tidal currents and 1-meter wave heights from a North Sea swell. Any exceedance of the position tolerance at maximum lift load would have introduced asymmetric loading that the seafastening structure was not designed to absorb. Weather window management is a critical operational constraint that most people never consider. Semi-submersible operations have strict sea state limits, typically a significant wave height of 1.5 to 2.5 meters for the most sensitive submersion operations. In the North Sea, where many of the world's largest oil platform removal and installation operations occur, sea states exceeding these limits occur for approximately 60% of winter days. Vessel operators contract weather forecasting services providing 7-day forecasts, updated every 6 hours, and operations are scheduled around weather windows that may only last 24 to 48 hours before conditions exceed operational limits. If conditions deteriorate faster than forecast during a submersion operation, when the vessel is already at 20 meters of depth with a partially loaded cargo, the crew faces a specific sequence of emergency decisions. Attempting to continue loading in marginal conditions risks cargo instability. Attempting to pump ballast out and resurface rapidly with a partially secured cargo risks different structural failures. Both options involve risk. The decision tree for this scenario is documented in the vessel's emergency operating procedures and drilled regularly, because it has occurred on real operations. The Dockwise Vanguard's 2013 transport of the Prelude FLNG topside modules, structures weighing over 70,000 tons, required 11 days of weather monitoring before a suitable loading window was identified in the South China Sea. The loading operation itself took 38 hours of continuous ballast management. The subsequent 5,000-kilometer transport to the installation site in Browse Basin, Australia, required 24-hour monitoring of cargo seafastening loads throughout the journey. Maintenance access during ocean transit is another underappreciated challenge. The cargo deck of a loaded semi-submersible is covered by the structure being transported, which may extend 40 or more meters above the deck surface. Access to the vessel's ballast tank inspection hatches, thruster maintenance access points, and structural connection points between the cargo and the deck requires working in confined spaces beneath a structure weighing tens of thousands of tons, in a moving seaway, sometimes thousands of kilometers from the nearest port capable of providing technical support. Maintenance crews undergo specific confined space and working under load training scenarios before deploying on heavy lift transport voyages. Now let's get into the facts that most people, including many maritime engineers, find genuinely surprising about these vessels. First, the MV Blue Marlin once transported an entire United States Navy ship. In October 2000, the USS Cole, a guided missile destroyer that had been severely damaged by a terrorist bombing in the port of Aden, Yemen, was too damaged to sail under its own power and too large for conventional salvage vessels. The Blue Marlin submerged its deck beneath the Cole, raised the warship onto its cargo deck, and transported the 85 zero-ton destroyer from Yemen to Pascagoula, Mississippi for repair. A ship transported a warship across the Atlantic. The Blue Marlin carried the USS Cole, 154 meters long, 85 zero-tons, as deck cargo across more than 9,000 kilometers of open ocean. The operation required 3 days of submersion and loading in the damaged port of Aden and 24 days of ocean transit to reach the United States. Second, some semi-submersible heavy lift vessels are used to transport other ships that are too large or too damaged to transit under their own power through specific waterways. The Suez Canal has specific draft and beam limitations. Ships that exceed these dimensions cannot transit the canal and must take the longer route around the Cape of Good Hope, adding approximately 9,000 kilometers to any Europe to Asia voyage. Several operations have involved loading an oversized vessel onto a semi-submersible to reduce the combined draft sufficiently to transit the canal, effectively carrying one ship inside the Suez Canal on the deck of another, smaller ship, to bypass the dimensional restrictions that would otherwise prohibit the larger vessel's passage. Third, the pioneering spirit is so large that it cannot enter most of the world's ports. Its 124-meter beam exceeds the width of virtually every commercial port's navigation channel. The vessel must anchor offshore and conduct all crew changes, supply deliveries, and equipment transfers by small boat or helicopter. This operational constraint means the pioneering spirit's crew of approximately 571 people can remain aboard for deployments lasting several months without the vessel entering any port. All provisions, spare parts, and crew rotations are conducted at anchorage, a logistical operation comparable in complexity to resupplying a mid-sized naval vessel during a deployment. Fourth, the structural engineering of the cargo deck must account for highly localized point loads from cargo support structures that no conventional ship deck could withstand. A conventional ship's deck is designed to distribute cargo loads over large areas using container stacking arrangements or bulk cargo holds. An oil platform's jacket support points may concentrate the entire 50,000-ton cargo load onto as few as 4 contact points, each contact point transmitting 12,500 tons of force through an area the size of a large meeting room table. The cargo deck plating and underlying structural framing must be engineered specifically for these concentrated loads, with reinforcement structures extending several deck levels below the surface contact points to distribute forces into the main hull structure without causing localized buckling or fracture. Fifth, and here is the controversial dimension of this industry. Semi-submersible heavy lift vessels are now being used at increasing rates for decommissioning aging offshore oil platforms, and the economics of decommissioning are creating a significant tension between corporate financial responsibility and environmental protection. Offshore oil platform decommissioning in the North Sea alone is projected to cost approximately $100 billion across the next 20 years, covering roughly 500 platforms that have reached the end of their productive life. Semi-submersible lift vessels represent the primary technical solution for removing these structures. However, the disposal question remains intensely contested. Removing platforms completely, as required under current international maritime law for most North Sea installations, costs significantly more than leaving them in place. Some operators and marine biologists argue that aging platforms, left in place and converted to artificial reef status, provide more ecological value than their complete removal, pointing to documented biodiversity around existing platform structures in the Gulf of Mexico, where the Rigs to Reefs program has left over 500 platforms in place as artificial reefs. Environmental organizations counter that artificial reefs normalize industrial abandonment of offshore infrastructure and set precedents that undermine decommissioning liability frameworks. The debate involves genuine scientific uncertainty about long-term ecological outcomes and genuine financial conflicts of interest from operators facing billion-dollar removal bills. It remains unresolved in international maritime policy. So here is what a semi-submersible heavy lift vessel actually is, stated completely. A 382-meter vessel that deliberately floods 200,000 tons of ballast water into its hull to sink 30 meters below the ocean surface, positions itself beneath a 50,000-ton oil platform, using 12 azimuthing thrusters, maintaining position to within 10 centimeters against open ocean forces. Lifts the platform clear of the water by pumping out all 200,000 tons of ballast in a precisely sequenced operation, lasting up to 72 hours. Secures a structure the size of a 40-story building to its deck, using custom seafastening frames and hydraulically tensioned lashing systems, and then transports it thousands of kilometers across open ocean at speeds up to 14 knots, with a crew of 571 people living and working beneath a cargo that weighs more than most naval warships. Every system on these vessels operates simultaneously at extremes that no other category of marine vessel approaches. Maximum submersion depth combined with maximum cargo load, combined with minimum stability margin, combined with weather window constraints, combined with dynamic positioning accuracy requirements. All at the same time, managed by computer systems and human operators who have drilled for every failure scenario their naval architects could imagine. The pioneering spirit removed the Troll A platform jacket, one of the heaviest offshore structures ever lifted, in a single 6-hour operation in 2015. A 40,000-ton structure that took years to build and decades to operate was lifted off the seabed and placed on a ship's deck in 6 hours, then transported to shore, then dismantled. Here is the question worth sitting with. If engineers can build a vessel capable of deliberately sinking itself 30 meters, sliding beneath a 50,000-ton oil platform in open ocean, lifting it onto a deck the size of 6 football fields, and carrying it across an ocean, what does that tell us about the actual limits of marine engineering when the economic incentive is large enough to justify the investment? Maybe the limits are never where consensus says they are. Maybe they are always somewhere further, waiting for someone to need something moved badly enough to build the ship that can move it. If this changed how you see the world, hit subscribe. We uncover the truth behind things you thought you already knew. Right now, somewhere in the North Sea, a semi-submersible vessel is at 20 meters of submersion depth. Its dynamic positioning system is firing 95,000 kilowatts of thruster power to hold it stationary against a 1-meter swell. Its ballast control operators are monitoring 40 tank valves simultaneously. In 6 hours, a 40,000-ton platform will be sitting on its deck. The ocean will not know it happened.